Okay, so my screen is visible, right? Hello?
Yes, yes,
Yes,
yes.
yes. Okay. So, good evening, everyone. I welcome you to the last problem solving session. So today we'll be revising the all the topics. So I have picked two, three questions, like picked few questions, selected questions from each of the graded assignment. So first we'll discuss those questions, and if we'll have time left, then we'll see. But I think so. So I'll start. So, so now, okay. So first question is this. So this is a bipartite. So we are given a bipartite graph, and you have the first question is asking if every Eulerian bipartite graph has even number of edges. So what do you think? Is it true or false?
True, ma'am.
So does everyone agree it is true? Okay. So why is it true? So the answer is true. But why? So first of all, what is an Eulerian graph? Euler, Eulerian, so Eulerian graph is basically we should be able to find a closed trail covering all the edges, and we have, so is there any necessary and sufficient condition for a graph to be Eulerian? So everyone knows, so there is some,
Degree is, I believe, n by 2, greater than n by 2.
no, we are talking about Eulerian graph. That, so for a graph to be Eulerian, the necessary and sufficient condition is that every vertex should have even degree. Okay. So so we have that Eulerian graph. So G is Eulerian if and only if every vertex in G has even degree. Now, now once we know this theorem, now can you prove that why every Eulerian bipartite graph will have even number of edges? So for, so hint, so if X is a bipartite graph, so that means we have two bipartition, A and B. So can we say that number of edges will be equal to degree, sum of degrees of vertices in A? Can we say that? Is it true that in a bipartite graph, number of edges is same as if we sum all the degrees of the one part bipartition? What do you think? Is it true or not?
True, ma'am. True.
Why is it true?
Handshaking lemma.
No, so handshaking lemma says that uh, if we sum all the vertices, then the number of handshaking lemma is 2 times E is equal to sigma dV. So handshaking lemma is 2 times number of edges is equal to sum over all the degrees. And this is because each edge is contributing 2 degrees. Each edge is contributing 2 degree to the degree sum. Therefore we say this is the handshaking lemma. But for bipartite graph, we can say this, that the number of edges will be equal to the sum of degrees of, if we just look at the vertices in A. So bipartite graph looks like this, and if we sum all the vertices, so this is A, this is B. If we sum all the degree of the vertices in A, then we'll see that we'll get number of edges. Why? Because 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 in a bipartite graph, every edge has exactly one endpoint in A. So each edge is contributing degree 1 to the vertices in the A. Therefore, we see that total number of edges is equal to total number of edges is equal to the, in a bipartite graph, it is equal to the sum of degrees is one of the bipartition. Now we are given that G is Eulerian and G is bipartite. Therefore G is Eulerian, that means every vertex has even degree. Moreover, G is bipartite, so number of edges is equal to sum of degrees in one bipartition. And since G is Eulerian, this is a even number, and we are summing even numbers. Therefore we see that number of edges will be even. So is the first question clear to everyone? Why every Eulerian bipartite graph will have even number of edges? So any doubts in the first one? Okay. So now, so this was for Eulerian bipartite graph. So we saw that since every Eulerian graph has all the vertices of Eulerian graph are of even degree, the next question is, so now if we move to the question 6, it says that is so is every Eulerian graph with even number of vertices will have even number of edges. So what do you think? Is it true or false?
True, ma'am. True.
Why? So see, Eulerian graph is saying basically that all the, so Eulerian graph is saying, so basically if we apply handshaking lemma, we'll have that sum of degrees is twice the number of edges. Twice the number of edges, V belongs to V. So now if it is Eulerian, we know that dV is even for all V. If we, Eulerian gives us that. Eulerian gives us that dV is even for all V. And moreover, we also have that even number of vertices. So we are adding even number. So we know that this term will be even. But the question is saying that number of edges is also even. So they are saying that sigma dV Vi belongs to V by 2 is also even for Eulerian graph. So from handshaking lemma, we see that we cannot directly conclude this. So now what do you think? Now do you think is it true or false? So everyone, like is everyone, so we are discussing question 6. It says that every Eulerian simple graph with even number of vertices has even number of edges. And we see that from handshaking lemma we cannot prove this. So now the question is it true or false? What do you think?
Is it true, ma'am?
Okay. So why do you think it is true?
As degree of V is even,
Yes.
even number of vertices and the even number of edges.
So no, see, so this is what
So
I was
if
saying.
it is
So from this we cannot from this we cannot conclude that. See, so we are getting that we are adding even numbers even times, but number of edges is this even number divided by 2, but that number can be odd also, right? Number of edges can be odd. So this
yes, 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 ma'am.
so this is false. Now you, like I am telling you this is false. Now try to construct an Eulerian graph. Suppose, so basically let's say I am saying suppose this graph has 6 vertices and 7 edges. So try to construct an Eulerian graph. So if it has 6, it is an Eulerian graph, so we are trying to construct the simplest one. So simplest one with odd number of edges. So let's take 6 vertices, and we have that all the vertices have degree, this has degree 2 and this has degree 4. So now if we sum this up, we'll see that sum is coming out to be 14. But the so number of edges are 7. So with this degree sequence, can you give me a graph? If we can construct a graph with this degree sequence, then this will be a counter example, because this graph, if such graph exists, that graph will be Eulerian, because all the vertices have even degree. That graph will be Eulerian. Plus it has odd number of edges. So now can you construct a graph with this degree sequence? So basically 5 vertices have degree 2 and one vertex has degree 4.
Ma'am, we can write all this degree in line, and then in the V5 we can have self loop also. So then 2
Okay. Uh, so we are avoiding self loop because we are considering simple graph. But in
okay.
but still, okay, so you have this, so suppose we have this vertices, so we have, so this is degree 2, right? So now we see that all these, so V1, V2, V3, V4, V5, V6. Now we just want one vertex to have degree 4. So maybe we can just do this, right? We connect this and this. So now this graph has degree sequence this 2, 2, 2, 2, 4. So this graph is Eulerian, but it has odd number of edges. So is this example clear to everyone that why the second, so the second question is false. That Eulerian graph with even number of vertices need not have even number of edges. So is the,
Yes, ma'am.
yes, okay. So okay. Then next question is, now look at this graph and we have to
Okay,
tell,
ma'am, in this number of edges,
yes,
is it odd, ma'am?
number of edges are odd, yeah, 7 edges. There are 7 edges. 1, so there are 7 edges. 1, 2, 3, 4, 5, 6 and 7, right?
Thank you.
Yeah. So now the next question is, what do is the following graph Hamiltonian? So first of all, tell me what is an Hamiltonian graph. Somebody tell the definition of Hamiltonian graph
We have to visit every node once.
and return back to the same place.
Yes, yes, we unwritten back to that is cycle. So
Huh.
Hamilton graph has a Hamilton cycle.
Cycle. So yes. So now do you think so if we have to check if the following graph is Hamiltonian or not. So what can we do? So for Eulerian, so for Eulerian graph, so okay, first of all, tell if this graph is Eulerian. First is tell question 7 if this graph is Eulerian. Will, because for Eulerian I have given you necessary and sufficient condition. So graph is this graph Eulerian?
No, ma'am, because there are node wherein the degrees are odd.
Such as,
D, if you take D, B,
yes,
3, 3.
yes. So if we'll take the degree of D, it is 3, which is odd. Therefore we know that this graph is not Eulerian. Okay, now we have found out that this is not Eulerian. Now second question is, if is this graph Hamiltonian? So for okay, so so if, if we have to show that some graph is not Hamiltonian, okay, so somebody said no. So why no, Serin? Why do you, maybe you can give an write the argument or something. So somebody is saying it is no, and it is the correct answer. So why the graph, why this following graph is not Hamiltonian? So if we have to show that some graph is not Hamiltonian, what do we do?
Ma'am, we have to remove the set by which C odd G minus S is more than that set, the cardinality of that set.
Not C odd, just connected components, because we are
Yes,
looking.
yes.
So correct. So he is saying that if we have to show that some graph is not Hamiltonian, it is sufficient to show that if we remove k vertices, after removing k vertices we are getting more than k connected components. If we are getting that, then the graph is not Hamiltonian. So so correct, this is the right argument. So but now you have to give a set. So basically G is Hamiltonian implies that if we take S as a subset of vertices and S is V1 Vk, then G connected components of G minus V1 Vk, number of connected components of G minus Vk should be less than equal to k. So this is a necessary condition. So if we have to show that some graph is not Hamiltonian, so if we have to show that some graph is not Hamiltonian, to show G is not Hamiltonian, choose k vertices whose removal will give you more than k connected components. So you have to do this.
But ma'am, removal is the trial and error only, na? Or we have some definite way to how to remove.
No, like it is by observation only. So if you have to show, so it is like a sufficient condition. Like it's not necessary that you will be always able to do this, but if you are able to find such a set, then you can directly conclude that this graph is not Hamiltonian. Okay. So Seren said no. Seren, do you have the set of vertices also whose remove you can type the set of vertices whose removal will give more components maybe? Okay, so first tell me, if I remove AFC, how many connected components are we getting? In this graph, if I remove A, F and C, how many connected components are we getting? That is, if we remove this, this and this, and if we look at the graph G minus AFC, how many connected components are we getting?
It's still connected. One component only will be getting. So if we remove additionally
So
A,
no,
C, H
no,
after
it is
that
not connected,
F
right?
and
It
K,
is so if we are removing AFC, we are getting two components.
two components. Yes, two components.
But then this set is not the right set because we are removing three points, but we are getting two components. So this is not the correct set. So maybe so you were saying ki additionally what do we need to remove?
Uh, K and H.
Yes. Okay. Right. So if we remove these vertices A, F, C, K, H, then what is the resultant graph? We'll see that all the vertices are becoming isolated. That is, the resultant graph is D, E, J, G, I, B. So we are removing 5 vertices, but we are getting 6 component. Therefore, this graph cannot be Hamiltonian. So is it clear to everyone? Why this
Yes.
graph? Okay, now lastly, so we have checked that it is not Eulerian. We have checked it is not Hamiltonian. What about bipartite? Is this graph bipartite?
Yes, ma'am.
Okay, so why is it bipartite?
The vectors which we have removed is one side can be taken, and another what are the edges neighbors
Okay,
that is left out will be the another part of the bipartite.
yes, good. So he has found two independent sets and all the so that is fine. But also we can if we have this or also there's a, so do we have nice characterization of bipartite graphs? Like, do we have some necessary and sufficient condition for bipartite graph?
Yes, no odd cycles.
No odd cycles. And we can see that in this graph there are no odd cycles. Therefore, this graph is bipartite. So this graph is not Hamiltonian, not Eulerian, but it is a bipartite graph. So is this question clear to everyone?
Yes, ma'am.
Okay. Now, so we have three graphs. We have three graphs. So now we have to check whether they are isomorphic or not. So first of all, if we have to check this, first we find out the degree sequence of all the graphs. And if degree sequence are coming out to be different, then we say that these graphs are not isomorphic. But if degree sequence are coming out to be same, then we have to look for some other reason. So in this is what about the degree sequence of all these three graphs? Are the degree sequence of all these three graphs same? So we have to check whether some graphs are isomorphic or not. So first step is to check the degree sequence.
So three regular graph, degree three.
Yes, correct, correct. So there are three regular graphs. So all these graphs are cubic graphs. So this have same degree sequence. So from that we cannot conclude. Now, what do you think? Are G1 and G3? So first of all, G2 and G3. Are G2 and G3 are G2 and G3 isomorphic? So clearly G2 is a bipartite graph. So if G3 is a so it is a three regular graph. So now so are G2 and G, so first question is if G2 and G3 are isomorphic. Are G2 and G3 isomorphic?
Ma'am, no, ma'am.
Why?
Ma'am, G2 is bipartite graph and
Hmm.
G1 is also bipartite graph. So if you see G1 and G2 is isomorphic
Okay. But why G2 and G3 are not isomorphic?
because G3 is not, ma'am, G3 is not a bipartite graph
Why G3 is not a bipartite graph?
Odd cycle.
Yes. So basically, if you have to say that some graph is not bipartite, you have to display an odd cycle. And we can see that one, two. So if we look at this is giving us an odd cycle. So we see that G2 and G3 are not isomorphic because G3 has an odd cycle but G2 doesn't. Okay, now so but now some if G1 and G2 are isomorphic, so if you are saying they are isomorphic, then you have to give the explicit isomorphism. So basically, you have to give the explicit map, and one can easily see, like we can, like one can draw this graph and like since it is an even cycle, first convert it into a bipartite graph, like convert, make it the bipartitions, and then see, then map the appropriate vertices, and from that it, you will see that it is coming out to be a, it is coming out to be isomorphic. Now G1 and G2 are isomorphic. G2 and G3 are not isomorphic. So this will also give that G1 and G3 are also not isomorphic. So 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 this question is also fine. Okay. Any doubts in this question?
So in this, G1 and G2 is isomorphic, no?
Yes. G1 and G2 are isomorphic. G2 and G3 are not isomorphic, and G1 and G3 are also not isomorphic. Yes.
Yes.
Okay. Okay. So next question is, so if G is a bipartite, so we'll look at each statement turn by turn. You'll tell me if it is true or false. So G is a bipartite graph with bipartitions U and V respectively. So first is saying that if G is a bipartite graph, then number of vertices in U should be equal to number of vertices in V. True or false?
False, false.
False, because we can have like some vertex, some few vertices here and this, so this is clearly false. Now second is sum of degree of vertices in U should be equal to sum of degree of vertices in V. True or false?
This was a false, ma'am. I can construct a graph wherein this is not true.
True, true.
Okay, so you are saying it is false. What is the graph then? So there.
If we take
Hmm,
U is a one node and V is a two node.
yes, okay,
So then the degree at U is two.
okay, yes. But here also degree is 1, degree is 1. So see, sum of degree of vertices, so this is x, this is y. So if you are summing of vertices in x, it is coming out to be 2. This example is not working. So we were, so this, so we discussed a similar example today. We discussed a similar proof today only. So now somebody said it is true that sum of degree of vertices in U should be equal to sum of degree of vertices in V. Then why do you think it is true? Can you give a quick reason why it is true? Yeah.
Before we have discussed, ma'am,
Yeah.
degree of vertex. By handshaking lemma, you said that bipartite graph.
Yes.
Summation of degrees of vertices is equal to the number of edges.
Edges. Yes.
So,
Yes. Yes. So
sum of the degrees will be equal.
yes. So basically what he is saying, so if we have a bipartite graph, if we have a bipartite graph with partitions x and y. So we already saw that sigma of all these vertices, if we are bipartition, if we are taking vertices of all by, if we are taking vertices of one bipartition, then this is coming out to be sum, this sum is coming out to be the total number of edges, and same for the y. Therefore since it is coming out to be the sum for total number of edges for both the partitions, therefore it is also equal. So for so our general handshaking lemma say that every edge is contributing uh, uh, to sum to vertex v1 and v2. But for bipartite graph, since all the edges has one vertex in x and one vertex in y, so contribution to the bipartition x of each edge is exactly 1. Therefore we see that this first is also equal to the number of edges, and the second term is also equal to the number of edges, and hence they are equal. So does everyone understand why it is true? Is it okay with everyone? Okay. Now, okay. So, and third one is also clearly false, that number of vertices in U should be greater than number of vertices in V, because we can have any number of vertices in U and any number of vertices in D. Now, the next question is that if G is a graph of order n and minimum degree is greater than equal to n minus 2 by 2, then G need not be connected. True or false? So, what do you think? Is it true or false? And there is one related question also, that if minimum degree is greater than, suppose the number of vertices are, okay, suppose minimum degree is greater than equal to n minus 1 by 2, then G is connected. So we have two statements, this statement and this statement. So are both, so what is, if what among these, what all statements are true and what all are false, or both are true? What do you think?
Second one is true.
Second one is true. Okay, yes, that is right. So do you know why it is true also? So let's first try to prove this. So first,
By theorem, minimum of G is greater than or equal to n minus 1 by 2. If G is connected, then only we give this statement.
okay, yes, there's a thing. So yes, also if we want to look at some quick proofs, so we are give, suppose like for time being, let's say that order even proof will also work in the same manner. Suppose number of vertices are odd, then we are saying suppose del v minimum degree is greater than equal to n, then the claim is G is connected. So if we have to quickly show this, how will we show this? So suppose let v belongs to G, let v belongs to G. Now v, since minimum degree of v is n, so it has at least n neighbors, and then we have some leftover vertices, vn plus 1, v2n. So now we have to show that, G is connected, what we have to show that if we pick any, so v is, that is there exists a path between, from v can be connected to any of these vertices. So we see that v can be connected to v1 till vn. Now what about, suppose v is not adjacent to vn plus 1, then how can we connect vn plus 1 with v? Is there a path between v and vn plus 1? So let V belongs to G, then del V is greater than equal to N. Therefore, V has at least N neighbors. That is V1, Vn. Now this has 2n plus 1 vertices. So this is n vertices. Now suppose these are the leftover n vertices. So we see that there exists a path between V and Vi. To show there exists a path between V and W1. Now minimum degree is greater than equal to n. So degree of W1 is also greater than equal to n. Now now if we know that degree of W1 is greater than equal to n, now can we find a path between W1 and V? Anyone? So we are saying that, so we we are showing that if minimum degree is greater than equal to n minus 1 by 2, then the graph is connected, and we are taking the case when the number of vertices are odd. So suppose they are 2n plus 1 vertices and the minimum degree is greater than equal to n. Now we have to show that there exists a path between any two vertices, or we can show, or equivalently we can show that from V there is a path to any vertex. So from V to V1 we have found a path. V to Vi there is a path which is the edge. But what about V to W1? Can we find a path between V to W1? Can we guarantee a path?
W1 has any if W1 has any neighbors with Vi only, there will be a path.
Yes, yes, you are right. So if we can say, if we can show that W1 is a has a VIs as one of the neighbors, then we have a path. That is, we can go to W1 to Vi, then to V. So now, do we have that W1 has to be a neighbor with one of these Vi? So we are minimum degree
So degree of W1 is greater than or equal
equal
to
to
n.
n. Yes. So the
That
and
means
these are
uh,
hmm,
these are n minus 1 vertices.
yes, these are n minus
W2 to
1 vertices.
W1.
And W1 and V are not
So
adjacent. Therefore, W1 has to be connected to some
there is
Vi. Therefore, we see that, and if
there
order
is
V
a
is
path.
equal to 2n, then the similar proof works. So now we have shown this, that if minimum degree is greater than equal to n minus 1 by 2, then G is connected. So we have shown the truth of this statement. Is it clear to everyone? This statement at least? Is this
A
statement
minimum
correct?
degree is n is long.
Yes, because I am taking this
Degree of the
order V
vertex
equal to
W1
2n
and
plus 1. So minimum degree is 2n plus 1 minus 1 by 2, which is n. Right? Therefore, so I am taking the odd case first. And I am saying that even case can be similarly proved. So for odd case, is it clear? So is it clear to everyone?
is
Okay. Now, but so this is true. So now the next question is, if this bound is strongest. So when we were taking minimum degree to be greater than equal to n minus 1 by 2, then we were getting G is connected. But what if we take our minimum degree minimum degree to be greater than equal to n minus 2 by 2? Then then can we say that G is connected or not? So if it was greater than equal to n minus 1 by 2, then we were getting that it is connected. So now the question is saying that can we improve this bound? So what do you think? Is it true or false? So let's try to see with the simplest example. Like, so since it is, so if we are taking, if we are taking n equal to 4, then n minimum degree is greater than equal to 1. So we have 4 vertices and minimum degree is greater than equal to 1. So can we say that graph is connected? So for this n equal to 4, so can you construct a counter example? When we have 4, can you construct a non-connected graph? Non-connected graph on 4 vertices whose minimum degree is 1. If we can do this, then this statement is true.
The cross
Sorry?
four vertices with cross or plus.
Grass as in?
It's multiplication symbol.
So you are saying this
The degree of every vertices would be
1. So if we look at
yes,
just
yes.
this
That's
graph,
what.
if we look at this graph, so this is satisfying this condition. N is 4, minimum degree is 1, but this graph is not connected. Therefore, we see that this bound, that minimum degree is greater than equal to n minus 1 by, like, the lower bound to say that G is connected, all to always guarantee G is connected, cannot be improved. So this bound is strong, because if we can look at just this example. So now, are these both statements clear? Both these statements are true. That is, if degree or minimum degree is greater than equal to n minus 1 by 2, then graph is connected. But if we take a smaller number, say n minus 2 by 2, then we cannot say. Then it can be connected also and not connected also. So is this clear?
If we take null graph, then also that is also a counterexample.
Null graph as in? So two
Like
vertices. You are saying two vertices?
no, you can take 4 and with 4 dots.
So if you are saying 4 vertices, then the minimum degree should be greater than equal to 1. Right?
Ma'am, 4 only dots. So that in that degree is 0.
Yes, degree is 0. So but we are trying to show this statement, right? Minimum degree. So we are trying to say this, that if, so that example won't serve as an example for this question, because this graph has 4 vertices but minimum degree is 0, which is smaller than this. So for this example will work. You cannot give that example, right? Null graph. So if you are giving null graph, then you give the two vertices. So if we are taking two vertices, then this hypothesis saying that minimum degree should be greater than equal to 0. So then if you are then for that is also true, that graph is also not connected.
One question.
Yes.
Suppose if a graph is an isolated graph, how to?
Isolated graph as in?
Suppose if a graph is isolated graph means
Hmm.
how to satisfy this theorem? How to check it, ma'am?
So you are saying that if no. So you are saying that you
Yeah.
are saying, is your question this, that if del g is greater than equal to n minus 2 by 2, I I don't understand, what do you mean by isolated?
Isolated means also a null graph. So no degree.
Huh.
Degree is 0. Suppose if same graph, but only one vertex is separately, not connected among the graph
So
vertices.
so you are saying this graph with just one vertex.
Yeah. No, ma'am. Many vertices are there. Also, some vertices are connected by edges, but
Okay.
only one vertex
Is
not connected.
isolated. Okay,
Yes.
like this. Okay. Huh. So your question, now your question is, okay. So see, so what is the so the question is saying that if a minimum degree is greater than equal to n minus 1 by 2, then the graph is connected. Okay. But this theorem, this statement is not saying anything when this condition is not satisfied. So if you see this,
Yeah.
so if you see this kind of graph, this graph has 5 vertices and minimum degree is 0.
0.
So this condition is not satisfied, right? Minimum degree is 0 and this condition is not satisfied, that 5 minus 1 by 2. So so this theorem is only conclude, like the second statement is only giving us an answer when this condition is satisfied, that is when minimum degree is greater than equal to n minus 1 by 2, then we can always say that graph is connected. But if this condition is not satisfied, then we don't know whether the graph is connected or not. Okay.
Okay.
and and the second
Yes,
part,
yes.
second part was saying that what if del g is greater than equal to, what if is del g is greater than equal to n minus 2 by 2, then can we always say that graph is connected? No. If this if this condition is true, then we have this example, either we can take n equal to 2, this example, n equal to 4, this example. So we see that both these examples are satisfying this condition but are not connected. So therefore therefore we cannot conclude that, so we cannot conclude that if such a graph is satisfying, if a graph is satisfying this condition, whether that graph is connected or not. Okay. So this was the problem, this was the question what was asking. So now is the confusion clear? So we are only able to conclude about connectedness of the graph if minimum degree is greater than equal to n minus 1 by 2. If a graph is not satisfying that condition, then we don't know whether the graph is connected, whether a general graph will be connected or not. Then we have to check by looking at the specific graph. But this condition is ensuring that if minimum degree is greater than equal to n minus 1 by 2, then we don't have to look at the graph also. Then we can directly say that that graph will be connected. Okay. So if this is clear, can I move on to next question?
Yes, ma'am. Yes.
Okay. So next question is, so is K3 a subgraph of K6? What do you think? Is it true or false?
True, ma'am. True.
Why? So okay. True, because if you take K6, all the vertices are adjacent to each other, and if we pick any three vertices and the subgraph induced by it, that will be K3. What about, so first statement is true. Yes, because we can just look at the subgraph induced by thing. Now what about 2? Is K4 a subgraph of K44?
True, ma'am. True.
So why? Now you have to give, if K4 is this, K44 is this, K44 is this. So if you are saying that K4 is a subgraph of K44, then you'll have to give a, then you give me 4 vertices which are forming K44. And if you think it is false, then you give me a reason why it is false. Why it is not. So K44 is basically, it is a bipartite graph, 4 vertices in one bipartition, 4 vertices in other bipartition, and all the vertices, all Vi is connected to Wi. So what, so is K4 a subgraph of K44? Yes or no? So there's an answer which says no. Okay, but why? You have to give a reason also why K4 is not a subgraph of K44.
Here V1 is adjacent to W1, W2, and W3 and W4.
Yes.
But if we choose four numbers, four vertices, then we cannot have a
Yeah.
V1 and V2 is not adjacent.
Yes.
Uh,
Yes.
so we will not be getting a subgraph
Yes.
K4.
Correct. Yes. Correct. So we see that if you pick any 4 vertices, we are not getting any, if any collection of 4 vertices are not giving us a collection in which all the vertices are adjacent. Therefore, K4 cannot be a subgraph of K44. What about third? Is K23 a subgraph of K44?
This is true, ma'am. True.
Okay, why is it true?
Because both are bipartite, and then K44 is bigger mesh as compared to K23.
So
So
basically,
definitely,
huh. So basically, you have to take 2 vertices from first bipartition, 3 vertices from other bipartition, and if you look at the subgraph induced by those vertices, then that will give us K23.
ma'am, the second reason I could not understand, ma'am. K4 is subgraph of K44.
So K4,
But
see, there's one reason that if you see any, uh, if you see any 4 vertices, you cannot pick 4 vertices such that, oh, so, so first of all, in K4, every vertex has degree 3, right? So if I'm taking some vertex, if I'm taking some vertex V1, if it, and it is adjacent to W2, W3 and W4 or W1, but but V1 is adjacent to the vertices V1 is adjacent to, but they are not adjacent within themselves. Or moreover, so by looking at a picture, you can say, or secondly, you can also see that K4, since K4 is a complete graph, it has a triangle. It has an odd cycle. So
yes, yes,
but
yes.
K44 cannot have an odd cycle. That can be other reason also.
But ma'am, you said K4 has maximum degree 3, but connection 4 means 4 degree at least for each node.
No, K4 has like there are 4 vertices, right? So but degree is 3. It is not connected to itself. It is connected to all other vertices. So K4 is this. So each vertex has degree 3.
Okay, okay.
Yeah. Okay. So this is clear. Okay. So now this is the question, next question, that G is a bipartite graph, then size of maximum matching in G is at least,
Third one, ma'am.
Third one.
That means
Mod
E of
EG.
G divided by delta of G.
Okay, good. That is the right answer. Now, why? Can you give us a reason also?
So that is sum of edges.
Hmm.
The size of maximum matching in G is a delta of Z.
Yes. So we have now, this is this. Now we have to show. Now we have to show that size of maximum matching in G is greater than equal to sum of edges by delta G. So first of all, we are given that G is a bipartite graph. So do we have any theorem which says that size of maximum matching? What does Koenig's theorem says? Koenig's theorem. Size of maximum matching in bipartite graph is equal to
Minimum vertex cover, ma'am.
yes, size of minimum vertex cover. Good. This is Koenig's theorem. Now, so now we have to show that size of minimum vertex cover is greater than equal to Eg by del G. Okay. So first of all, what do we mean by vertex cover? What do we mean by vertex cover?
A set of vertices such that every edge is incident to.
That is, every edge in G is incident to at least one vertex in S. Now, is there any relation between sigma dv v belongs to S and where S is the vertex cover? Okay. So here S is the minimum vertex cover. So I'm asking, is there any relation between these two terms? What is less than so what is less than equal to? So there is a so basically
Can we apply handshaking theorem?
a handshaking theorem. Okay. So yes, what how do you want to apply the handshaking theorem? Yes.
The sum of degrees of vertices equal to 2 times of edges.
Yes, but that is for all the vertices, right?
Yeah.
Now we are just now I am just saying that we are just picking the vertices in the vertex cover. Is there any relation now? So in vertex cover, so we know that every edge is incident to at least one vertex in S. That means if you have an edge, it is contributing at least 1 degree to to some vertex in S. So now what should be the relation? Is the sum of degree V greater than equal to number of edges or less than equal to number of edges? So,
It is less than,
Less than or equal to.
okay, so
less than.
this one or less, which one is less than, which is a smaller term? Okay, let me ask, which is a smaller term among these?
Sum of degrees, ma'am, is smaller than edges.
So you are saying sum of degrees is, so we have sum of degrees is smaller than the edges. So does everyone agree with this? So think about it again. So what is the vertex cover? So suppose this is the vertex cover, right? V1, V2, Vs is the vertex cover. Now if you, so there can be two, there can be, so suppose if E is an edge, E is an edge, E is an edge in G by say V1, V2. So then what do we know? If S is a vertex cover, then what do we know? That either we know that v either v1 will belongs to s or v2 belongs to x, or both also cannot, both also can also belongs to s, right? Because if s is a vertex cover and e is an edge, then this vertex cover says that every edge is incident to at least one vertex in s. So this will say that so by definition we'll have that at least one of v1 or v2 is in s. So if a v1 v2 both are in s, then it is contributing some 2 to this LHS. If only one of them is in s, then it is contributing some of 1 to the LHS. Now what do you think, what should be the relation? So is either contributing each edge is either contributing plus 1 to LHS or plus 2 to LHS. If only one of this vertex is in the vertex cover, then it is contributing plus 1 to LHS. But if both of these vertices are in vertex cover, then it is contributing plus 2 to LHS. If each edge is doing this, then what should be the relation? What is the smaller term?
Then edge is the smallest term. Then
Yes,
is
then
then
edges
edge.
is a smaller term, because one edge can contribute either 1 or 2 to LHS. So is it clear? So we see that this is wrong. We have that sum of degree of vertex is greater than equal to edges. So we have shown this. So is this statement clear to everyone?
Yes, yes.
Because each edge is contributing plus 1 or plus 2 to LHS. Now if this is also, this is degree, so it will be less than equal to the maximum degree. So we get that number of edges, so we have maximum degree and order s, so we see that number of edges is less than equal to order s
எடா
into
ஆனா எனக்கு இது இல்ல
delta v.
நெட் இல்லடா இந்த பேட்டரி
And
முடிஞ்சு
this was
போச்சு
what we were trying to show. So we have
சண்டே
shown that
எக்ஸாம்டா
s is greater than equal to modern E by
நாங்க
delta
6 வருஷத்துக்கு ஒரு
V.
எக்ஸாம் பாஸ்
And this
பண்ணணும்
was the size of minimum vertex cover. And since it is a bipartite graph, it is also the size of
அப்புறம் சொல்லி
maximum
தரேங்கடா ஆனா
matching.
வெளியில வர இப்ப
So we have shown this. So is it clear
பேட்டரி
to everyone the proof?
Yes, ma'am.
100 மார்க்ஸ்க்குடா
Any confusion? Okay. Okay. So this is a similar question. Then if G is a graph with n nodes, then size of maximum independent set in G is always greater than equal to
What is independent set, ma'am? I forgot. Independent set.
Okay. Independent set is basically, independent set is set S of vertices such that there is no edge between any of these vertices. So in bipartite graph, when you have A partition, B partition, A is independent, B is also independent. S of vertex such that there is no edge between vertices of S. So we'll see that the answer for this one is the first one. Okay. Does anyone know why is it true?
Can we take one little example and then prove that this is the true? Then, because proving may not be possible in exam.
Hmm. Okay. But yeah. Oh. Okay. Yes, we can do that. So see. So basically, what it is. So we have. So basically, yeah. Suppose we have a graph G, and we have to show that size of maximum independent set is greater than equal to n by del G plus 1.
We can take small example like
Hmm.
K22.
Yes, if we are taking K22 or KMN only. So K in KMN, what is the size of largest independent set?
It depends upon M or N, ma'am, which is the largest.
Yes, so suppose, so it is maximum of Mn, right?
Yes, yes.
Yeah. So we see that, so it is maximum of Mn. So suppose M is greater than equal to N. Then for this inequality should follow, because M, so size of maximum independent set is M, and it is greater than equal to, what is the number of vertices? Number of vertices are M plus N. And what is the maximum degree? What is the maximum degree of this graph?
Which is smaller.
No, maximum degree, the bigger one, right?
Yes.
So M. So we see that M is greater than equal to, wait, this is size of maximum independent state. Uh, so,
Can we take 2 to K22 and then we will prove this?
okay. So if we are looking at K23, say, so if you are taking K23, size of maximum independent set is 3. Total number of vertices are 5. Total number of vertices are 5. And maximum degree is 4. So, but this is not coming. Wait, let me check.
Why maximum degree is 4? Maximum degree is 3, huh?
Uh, Yes, maximum degree is 3 plus 1. I am saying 3 plus 1. So it is, I think, del G minus 1. Wait. I'm
It is coming, ma'am. Three
3,
three is greater
then
than 5/4. It is coming up.
no, 5 by 4 is 1 point something, right?
3 is greater than 5/4, na, ma'am?
Oh, yes, yes.
Independent
Oh,
set.
sir. Yes, fine. Sorry. Yes, coming. Okay. Yeah. Okay. Yeah, it is coming. Ah. So, but this is okay. So the so basically, okay, so in this question only, if it is say K53, and if we have to find an independent set, so how do we find an independent set? So how, if we want to find an independent set, how will we do? First we'll pick some vertex 1, right? So if we are picking some vertex 1, then we'll look at its neighbor. If we look at its neighbor, so now if V1 is belonging to S, then the next vertex which is in the independent set should not be its neighbor. So next vertex will have to find from V minus the neighbor of the V1, which is these many. So basically then we'll have to find from 8 minus maximum degree 2. So 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 basically what we are doing is we are trying to we are trying to construct independent set inductively. So first we pick some vertex v1, then we if we want to pick another vertex v2, then we have to pick it from something which is not from its neighbor, and we'll keep on doing this. And if we'll do the calculation, we'll see that the bound that we are getting, it will be n by del g plus 1. So we are trying to construct the independent set inductively, and using your examples also you'll see that this is the condition. Okay, so now next question is this, that if G is a bipartite graph without isolated vertices, then what is the size of minimum edge cover?
Size of the maximum matching in G, ma'am.
Oh, so size, if it is a bipartite graph, then minimum vertex cover, sorry, minimum, okay, no, sorry. So yes, minimum vertex, size of minimum vertex cover is equal to size of maximum matching. That is Koenig's theorem. But size of minimum edge cover is not size of maximum matching. So I think you were using, so Koenig's theorem says this, that if we have a bipartite graph, then minimum vertex cover, size of minimum vertex cover is equal to size of maximum matching. Now, so therefore you cannot directly conclude from this that this it will come out to be size of maximum matching. But is there any relation between size of maximum matching and minimum edge cover? Is there any relation between maximum matching and minimum
Their
edge
sum
cover?
is number of vertices.
So their sum is,
The number of vertices.
yes, size of maximum matching plus size of minimum edge cover is the number of vertices n. And this is because this is true only when the graph has no isolated vertices. So if graph has no isolated vertices, then we see that size of maximum matching plus size of minimum edge cover is equal to the number of vertices, which is say order v. Now, so that means we get that size of minimum edge cover, what is the size of minimum edge cover? Is order V minus size of maximum matching. And this is a bipartite graph. So by Koenig's theorem, this is order V minus size of minimum vertex cover. So now do we know this? What is this number? Number of vertices minus size of minimum vertex cover. Do we have some relation between maximum independent set and minimum vertex cover? Do we have any relation between them? Maximum independent set and minimum vertex cover. So here we have this relation that size of maximum matching plus size of minimum edge cover is equal to number of vertices. And similarly, we also have the analog for vertices also, that size of maximum independent set plus size of minimum vertex cover is equal to order V. Therefore, we see that order V, number of vertices minus size of minimum vertex cover, is the size of maximum independent set in G. So we are using three theorems. We are using, first of all, we are using Koenig's theorem, which says that size of minimum vertex cover is equal to size of maximum matching. And then we are using the relation between size of maximum matching and minimum edge cover, and size of maximum independent set and size of minimum vertex cover. So if we use these three relations, then we are getting our answer. So is this question clear to everyone? Is it clear to everyone? Okay. Okay, I think I skipped something. Yeah. So now there's one also. So minimum spanning, we have to find minimum spanning tree using Prim's algorithm, which is starting at vertex E. So is everyone aware of Prim's algorithm?
We have to choose from any vertex. What is the smallest weightage of edge should
Yes.
be chosen first,
Yes.
and then
Yes. So in this question, we are given that we have to start from vertex E. Yes. So now we have to find a minimum spanning tree. We are starting from vertex E. So what should be our next step using Prim's algorithm?
We have to keep E in one set and all other in other set. Then we have to find the minimum weight.
Yes. So if we pick, first our initializing is E. So we are keeping E in one, and we are keeping E in one set. So we are basically looking at this cut. We are looking at this cut. So now what is the minimum cost edge? Minimum cost edge in this cut. So we have
4.
S is equal to T E and S bar is equal to V minus A. So it is 4 because all the only edges are EA and EF, and EA is the, so we'll add this, edge R in our minimum spanning tree. So our first edge is EA. So first edge is EA. Now if our edge is EA, now what is the next step?
We have to keep EA in one set and then all another set.
So
Then
yes.
we have to again see which is the minimum.
So now our cut is this. So now our cut is this. So what is the minimum edge now?
AB.
So does everyone think the edge is AB? Yes. Okay. So basically now S bar is V minus EA, and we have to look at the minimum cost edge CE, which is basically the edge with one vertex in S, other in S bar, and has minimum cost. So if we have EA in first set, and we have B C D F G H in other set. So what are the edges going from E? We see that there's an edge from E to F with weight 5, and there's an edge from A to B with weight 6, and there is an edge from A to B to edge 1, and A to F to edge 6. So among this, AB is the minimum weight. So we see that the next edge that we are going to add is AB. So AB is the next edge. Now we repeat this process. So now the set S will be EAB, and set S bar will be the rest of the vertices. So now what is the minimum cost edge now? So we'll do this only. So we have three vertices here, EAB, and rest other vertices there, CDFGH. So what is the minimum cost edge in this cut?
BC.
BC. Yes, because yes, BC is the minimum edge. So the next edge that we are going to add is BC. So now we have T3 is EA, BC, AB. Now the new cut is EABC, and then we have D, E, D, F, G, H. And in this new cut now, what is the smallest weight edge? So we see that we have E. So the numbers which are there are EF is 5, A, AF is 8, BG is 6, BF is 6, and CD is 3, CG is 2. So now what is the minimum weight edge of this cut?
2 CG.
CG. So the next edge that we are going to add in the minimal spanning tree is CG. Okay, so now the new cut is E, A, B, C, G, and then we have D, F, H. So we have BC is 3, F, FG is 1. So we are getting some one edge. So we see that this is the minimum. This is the minimum in the next step. So now we have to compute the last edge. So we have the new cut is A, E, B, C, F, G, and D, H. So now what is the minimum cost edge in this cut?
G GH is also minimum and GD is also minimum.
GH is also, yes. So we can take any of these. So are we done?
No, no, one H is
One.
also needed.
So it is still not a spanning tree because one vertex is not covered. So now what is the next edge then?
GH.
GH. So is Prim's algorithm clear to everyone? Like how to find a minimal spanning tree using Prim's algorithm?
Yes, ma'am.
Okay. So now we have that. Suppose we are running. So this was Prim's algorithm. We also have a Kruskal algorithm. Now suppose we are running both of these algorithm and both these algorithms are producing minimal spanning tree. Then which of the following is true? So Kruskal algorithm is providing minimal spanning tree Tk and Prim's algorithm is providing minimal spanning tree Tp. So first claim is that TK and TP are identical. True or false?
This is false, ma'am.
False.
False. Okay. But what if they, okay, so this is false because because minimal spanning tree is not unique and we can get either of those. We can, if we so first statement need not, first statement is false. What about the second statement? If E is a minimum cost edge in G, E belongs to both TK and TP. True or false?
Yes.
This is true, ma'am.
Are you sure? It is saying E is a minimum. It is not saying E is the minimum. So it is,
Okay.
so it, that means it is one of
Then
the minimum edges.
yes. And then it is false, ma'am.
False. So you have to like carefully read the question. It is saying a minimum. That means it is saying it is, it need not be the unique minimum. So then it is, it need not be true because there can be two minimum cost edges and one can go in one and other can go in other. So second statement is also not true. Third statement is if TK is different from TP, then some pair of edges in G have same weight. True or false?
This is, ma'am, true.
Why it is true?
Because as we know that we may have two different spanning trees for a single graph, but the cost is same for both. So that means there are some edges which are same.
No, no. So this, some pair of edges in G have no, no. This question, this is saying that if we are getting two different minimum spanning tree, then it is, then two edges can have same weight in a graph. It is not, then it is not like, so basically if a, so it is saying that if a graph all edges have distinct weight, then both the algorithm will give the same spanning tree. So what do you think? Is it true that if all the, if we have a direct, if we have a weighted graph in which all the edges have distinct weight, that is there is no two edges have same weight, then the minimal spanning tree will be unique. What do you think? Is it true or false?
Then it is true, ma'am, if every weight is unique.
Huh. Because if every weight is distinct, then then the minimal spanning tree is unique. So this is just the contrapositive of this statement. So if it is saying that if we are getting two different spanning trees, if we are getting two different spanning trees, then at some of the edges should have same weight, because if all the edges have different weight, then the spanning tree should be unique and we should be getting the unique answer. So we see that third statement is true. And what about the last statement?
False.
Okay. So for third statement is true. So false. If E is a maximum cost edge in G, E belongs to neither TP nor TK. So you are saying it is false. Why is it false?
Like if the maximum cost edge is a bridge edge, then it has to be in the
Yes.
span tree.
Yes, you are right. So basically, if we have some maximum cost edge which is a bridge or which is not contained in any of the cycles, then it has to be there in every spanning tree. So therefore it is false. Good. And third was true. So I was writing the reason. And third was true because if all weights are distinct, then MST is unique. Okay. So now, so we have another question. So now consider an undirected graph, and in this we are given that every edge has distinct weight. And edge CD is the edge with minimum weight edge, and edge AB is the edge with maximum weight. Then which of these is true and which of this is false? So first statement is that every minimum spanning tree must contain CD. True or false?
It is true.
Yes,
It is true. It is true because it is now
True.
because now,
the distinct weight.
yes. And also, if we have a unique minimum cost edge, then it has to be there in every spanning tree. What about the second statement? If AB is in a minimum spanning tree, then its removal must disconnect G. True or false? So AB was the maximum weight edge. Okay,
True.
why is it true?
Because if it does not, then there's an other edge that will have obviously lesser cost.
Yes, there's an another path, not in need not be an edge, there's an another path, and we can, so basically we can add some another edge with lesser weight. Therefore we see that it's, so this is also, so second statement is also true. Then third statement is no spanning tree contains AB. True or false?
It is. It is. It is. Uh, it is because
False.
AB is the maximum, ma'am. AB is the maximum, so it is false.
So no minimum spanning tree contains AB. It is false because if so, like in the last question, if AB is a bridge, if AB is a bridge, then AB has to be in every MST. And the last is G has a unique minimum spanning tree. This we already discussed that if all the edges have distinct weight, then the spanning tree is unique. Okay, this is now. Okay, now. Okay, so first let's discuss the last one because there's so first question is, if now we are talking about chromatic number and chromatic index. So I am just recalling. So chromatic number, which was chi g, it was the minimum number of colors required to color vertices of G. And chromatic index was chi prime G, which was minimum number of colors required to color edges of G. So now first question is, if G is obtained by adding a vertex S to K34 which is adjacent to all other vertices, what is chromatic index? What is chromatic index? So before doing this question, so we have this K34. So we have K34. So can you tell me what is the chromatic index of K34?
Four.
This is two. So chromatic index is Four, ma'am. Four.
Maximum of 3 comma 4.
Yes. So first of all, chromatic index is either maximum degree or maximum degree plus 1. In this, maximum degree is 4. So it will be either 4 or 5. So but for bipartite graph, what is the chromatic index?
Of delta of G.
It is maximum, ma'am.
Yes.
Maximum. Delta G.
So for for chromatic number, okay, sorry. So I'm saying so I'm saying that chromatic number of K34 is equal to maximum degree 4. Now, but the question now is asking, so we have this K34, okay? So we have this K34, and now we have also an additional vertex S. Now we have this, so this is K34. So in this, all the vertices are adjacent. So plus more this is K3, 4. Now we have now the new graph is this. We have one vertex which is adjacent to all other vertex. So now in this new graph, what is the maximum degree? In this new graph, what is the maximum degree? K3, 4 is
7.
S. What is
Right,
the
5.
maximum degree?
Ma'am, it is, if you see the node S, it has 6 degrees.
Oh, okay, there's one more. Yeah, yes. So what is, so now we have a node which is attached to every other vertex.
So maximum degree is 7 then.
Maximum degree is 7. Now question is, what is the chromatic index? What is the chromatic index of this graph? So for K34, we know that chromatic index is 4. Now for this new graph, first of all, it can be either 7 or 8. Now question is it 7 or 8?
It is 7. It
It
is
is 7.
7.
Why is it 7?
The 4 vertices can be 4K in K34. The 4 vertex can be colored with one more color because the degree is 3. So we can color all the 4 with
Oh,
adjacent
no,
some
no.
other.
Sorry, but oh, so we are talking about chromatic index.
Yes,
We are
yes. Chromatic
coloring
index.
edges. We are
Edge.
coloring edges.
Yes, ma'am.
Hmm.
The degree of each 4 vertexes is 3, ma'am. So one more color is left. So from S to that 4 vertex, we can color with some other color, which is already given. So only 3 more new colors needed. S is
Ma'am, we have maximum
adjacent.
color theorem, which is 7, which says any graph is maximum color theorem 7. So that we can use.
Okay, we don't want to use any theorem. So first of all, we are coloring edges. So okay, you were giving an argument. So sorry, like I was. So you are saying we need 3 more colors. Why do we need 3 more?
3
We
more
just
color.
uh,
Because this
huh?
4 adjacent to 4
Okay, wait.
right
I
hand
will
side.
first label the vertex. Then it is easy to understand. Yeah. So if this is So now what you are saying? Yeah.
Uh,
Hmm.
So W1 is of degree 3. So it is already colored with 3 colors.
Yes.
So from
Okay.
S to W1, we can use that one more color
Fourth
which is
color.
not adjacent.
Yes. Yes.
Fourth
Okay.
color.
Yes.
So
Fourth
that is
color.
possible for all the 4.
So, but see, suppose I choose this fourth color,
W1, W2,
but
W2.
how will you ensure? But how will you ensure that we are not choosing the same color for those for those edges? So,
Because K34, no ma'am. K34 we'll use maximum 4 colors. So it will be definitely each vertex will be of 3 different colors. W1.
We are talking about edges. Edges we have to
edges
color.
we have
Ah,
like see, I get it what you are saying, but I'm saying that that argument might not work in this
work.
sense. Suppose,
Okay.
suppose this is C1 color, this is C2 color, this is C3 color, then you're saying let's give it C4 color. Okay, W1 wala. Now W2 hai. Now if we have W2, So here also there are some three colors used. So what is the so that okay, so W2 has three colors. So these three colors can be all different colors also, right? So suppose this is the different colors. Suppose all these colors are different. C4, C5, C6. Then you have used all the colors, right? So you'll have to give another argument. Are you are you understanding what I'm saying?
Ah, yes, ma'am. Yes, ma'am.
Hmm.
This argument is not possible.
Yes. Yes.
Is it 8, ma'am? Then
No, the answer is 7. But you have to give a reason why
so,
seven colors are sufficient. Okay, so let me like use like so first of all we see that K. So first of all K44 is a okay, can we no what I'm saying is
can I say this?
yes, yes, yes. So yeah, so you
Um,
are giving an okay. First you give an argument, then yeah. What is your argument? Yes.
from S to W1, W2, and W3 and W4, four colors will be given, and
But okay, so
three
see,
colors will be given to V1, V2, and
huh?
V3,
But you have to
which will be different.
no, no. But the problem is this. So see, if you are you have to ensure the four colors. So basically the color that you are giving to the edge S to W1, it should be different from the color which is given to W1 V1, W1 V2, and W1 V3. And similarly, the color that you
Ma'am,
are giving to
we can start
SW2.
with, ma'am, sorry,
Seven different colors, ma'am.
we can start with S node, and because we can take seven different color from S, because seven is the maximum degree. So then we have to use that color from the bottom of the graph. Then
Then also
definitely we
you'll
will.
have but definitely you have to give a reason, right? See, so then also there is a problem. So you if you have used seven colors, then you'll have to ensure that the three colors that you are using here, uh, so basically there is no overlapping. So there are other so we have to keep in mind these the colors that are already assigned also.
Yes, ma'am.
So like do you see like why your argument, so your argument is bit little bit incomplete, like it's not complete, right? Or do you,
Colors will be given from S to all the
huh?
partitioned
but
vertices.
yes, that will be given, but we also have to ensure that we are giving that color, the color that we are giving should be different. But how can we so see, like she was pointing out, so suppose you are giving, so see we run into trouble like this. If this is W1, this is W2. Suppose I give color, so W1 is giving suppose color C1, C2, C3. I can now I have so this K34 I have colored with C1, C2, C3 and C4. Okay. So now for CW1 I have four options. I can either give it C4, C5, C6, C7. So suppose I give it C4. Now for W2, there are three colors. W2 also there are three colors. So since I am giving it C4, so for W2 there are three colors. What if these, so it will be either C1, it will be either from C1, C2, C3, C4. So I can give color say C5. C5 color is not being used yet. So I'll give C5 to W2. So C1, C2, C3, C4 color was already being used by K34.
Yes, ma'am.
So I am giving C5 to W2. Okay.
Yes, ma'am.
Now and suppose yeah, so and similarly I am giving C6 to W3 and C7 to W4. So till
W4.
now it
Yes.
is fine. Till now it is fine. But now when I am at now but when I'm at V1, what is the guarantee that the four colors that we are give that? So now also, okay, for V1 also we have four colors here, and so we can give one color to this one. Four, no, sorry, four colors here and four colors here also. So what is the guarantee that we can find the colors?
Ma'am, please solve it because now only 10 minutes are left. So we have to
Okay,
finish also. You
okay,
give us answer, we will cram that. You will remember that. Seven. Seven is the answer for this.
yes, okay. So I'll just quick, like, so I'm just so what I was saying. So suppose this is the S vertex, right? So okay, so this was V1, K4, K3 4 it was there. V1, V2, V3, V4, and W1, W2, W3. So this is the S vertex. So first I am saying, let's just look at K44. K44 is a subgraph of this, right? So K44 can be colored by four colors. Suppose I have colored K4 by C1, C2, C3, C4. C4. So now I have just three colors. Now I can just give S. So now I can just give C fifth color to SW1, C6 color to SW2, and C7 color to SW3. So basically I am saying that uh, if we are attaching K34, instead of attaching S to all other vertex, first let make it K44 and then color it with using four colors. Then we just need to give three more colors and we can give it. So hence the answer is 7. So is the argument clear?
Yes, ma'am. Yes.
Is it clear to everyone? So first what we are doing is, so we see that the result, the original graph that we want to color is a has K44 as a subgraph, and we know that K44 can be colored by four colors. Now we just have three edges left, so we'll give three different colors to those three edges.
Okay.
Okay.
Yes.
Yes, ma'am.
Yeah.
Now understood.
Okay. Okay. So this. So was everyone able to show that this is a planar graph? This is a question from your assignment also, or so I'll just
Yes, ma'am. Planar.
planar. So if such graph is there, you just try to see
Ah,
whatever the lines are intersecting, you try to make them outside, bring them outside.
yes.
So you'll see
Ma'am,
that.
in this, but ma'am, in this, if we use that 2v minus 4 identity, edge is less than,
Hmm.
so that is not satisfying. So that is why I said it is a not planar, but answer is planar.
But see that.
Planar. In ma'am, last class you showed how to draw
Yes,
the lines outside. Using
yes,
that, it is planar.
yes. So Anupam,
No,
you
no, ma'am.
but
See, my
hard.
point is we have to
I
see edge.
Yes, yes.
We
Okay,
how many
Anupam.
we are?
Hmm.
How many? That is 8. So 2 into 8 minus 4.
Ha,
So that is.
but that rule is true for a planar graph with no triangles. This graph has triangles, so you cannot use that identity. So you can so that is that you cannot use. So the question is, if G is planar, then a number of edges. If G is planar, then number of edges are less than equal to 3v minus 6. So you have to use this identity, but so what you are using is wrong. What you are using is, with if G is planar with no triangles, then the number of edges should be less than equal to 2v minus 4. But since this graph has triangles, so you cannot, and if this inequality is not satisfied, so then you cannot conclude that it is not planar from this. Is it clear now? So you cannot use the second condition if a graph has triangles.
So ma'am, if we use first one, the 3 into 8 minus 6, that is 18. So
Yes.
but edges are not 18.
Edges, how many edges are there?
17. 17.
So
I
the,
counted.
so that inequality is satisfied, right? 17 is less than equal to 18.
Yes, yes.
Yeah. Yeah.
Ma'am, in the previous page, second question answer.
Sorry. Uh, Previous page.
Yes, ma'am.
Oh, okay, okay. There was a
Symmetric
second
index of
question
K
also.
to N minus 1. Yes.
Oh, yes, yes. Okay, yes, yes. I'll do. Sorry. So, yeah. So let's try with it for some odd example. So we have to find the index for a K2N minus 1. So K3. What is the index for K3? Chromatic index for K3.
It is 3, ma'am.
3.
3.
3, 3.
3. Right? So we have to edge it differently. So that is obvious. Now for K5, what is the chromatic index? First of all, for K5, what is the maximum degree?
4, ma'am.
4.
4. So what are the two possibilities? It will be either
4 or
4
5.
or 5. Right? So now what now it will be either 4 or 5. Okay? So this so now we have to say the chromatic index is 5. So chromatic index of K5 is 5. So we have to show that it cannot be colored using 4 colors. So this can be done. So suppose we have color C1. So tell me, what is the maximum number of edges that can be there with color C1, with one color? Maximum number of edges with one color. So first of all, can you have 3 edges of same color in this graph? Can you have 3 red edges in this graph?
No, ma'am. Maximum 2.
So maximum is 2.
2.
But there and how many so maximum is 2, and how total number of edges in K5 is? Total number of edges in K5 is
10, ma'am.
10. So that means we need at least 5 colors, right? Because so one color can be used to color at most 2 edges, and there are 10 edges, so we need at least 5 colors.
Yes, ma'am.
So is it now we want to generalize this? So for K, so we have checked it for K3 and K5. Now we have to generalize this. So now suppose K2N minus 1. So how many edges can you, so one color, say how many edges can, maximum number of edges of one color. Maximum number of edges of one color in K2N minus 1. What should be the maximum number of edges? It should be N,
N, ma'am.
because N, if you have N edges, and no two edges have a common vertex, so we have covered 2n vertices. So we can see that maximum number of edges of one color in K2n minus 1 is n. So is it clear to everyone, or is there any confusion in this portion up till now? So this is the key point here. That's why I am asking. So is it clear to everyone why maximum number of edges of one color in K2n minus 1 is n?
Ma'am, once again, ma'am, once again.
Yes. So see, in K5 did you understand why the maximum number of edges should be 2?
Yes, yes. Because 10 edges, maximum 2.
No, that is fine. But did you understand this? Like why maximum number of edges of one color should be 2?
Yes, I understood.
So now you have 2n. So if you have, oh, so this is 2n plus 1. Sorry, I'm taking 2n plus 1. Sorry. Now if you have 2n plus 1 vertices, so how many edges can you have of one color? N edges, right? Because n edges will cover 2n vertices.
2n vertices.
So
Yes.
so
Yes.
n edges. So maximum number of edges of one color in K2n is n. And now what are the total number of edges in K2n plus 1? It is 2n plus 1 into 2n by
2n divided by 2.
2. So that is n into
2n
2n plus 1. So now, so that means we need at least 2n plus 1 colors. Because one color can be used to color at most n edges, but we have n into 2n plus 1 edges. So therefore we need at least 2n plus 1 colors. And since 2n plus 1 is equal to del G plus 1. That is the maximum bound that we have. Therefore, we see that the chromatic index for K2n plus 1 is also 2n plus 1, is 2n plus 1. So, is it clear?
Yes, yes.
Okay. So, yeah, this is okay. So, we have done this. This is plainer. So, were you able to do this question? Were everyone able to do this question?
Yes, ma'am. Yes.
So, what is the maximum degree here in this graph?
4.
4.
4.
4, 4.
4. So, maximum degree. Okay, sorry. Maximum degree is 4. Yes. So that maximum degree is 4. So we know that chromatic number should be less than equal to 4. So first of all, first of all you see, since it has an odd cycle, therefore we know that it should be greater than equal to 3. So now we have only two possibility. It is either 3 or 4. So did anyone try this? So what was the answer coming?
XG is 3, ma'am.
Xt is 3. Yes. So you can see, like we can see that it will 3. So how do we see it is 3? So let's try it. So suppose this is an odd cycle. So we need three colors. Say R, blue, green. Now we have R, blue, green. Now this edge, so if you look at this node, red color and green color, red, blue, green. Okay. Oh, so sorry, we are first looking at the vertices. First we are looking at the chromatic number. So this is R, this is blue, and this is green. Now what is the possibility for D? Since green and
R.
blue are
Red.
adjacent, it's
R.
R. And what is now for F we have, similarly we can, for F we can only give B because
Blue.
blue. And now for E,
Green.
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 So we see that we are able to cover it with three edges. Now we have this ident. Now what about X dash G? We know it is either 4 or 5. So first let's try to cover it with 4. So if we want to cover it with 4, we look at the vertex with the maximum degree. Vertex with maximum degree is C. So first we'll give different colors to all those edges adjacent to that maximum degree vertex. Suppose red, blue, green, orange. And now we try to color it. So what is, so red, blue, green, orange. So now what should we give to AB? We can either give blue or green. So for without loss of generality, let's give it blue. Now what about this? So
Green.
we can give it
A we can give green.
green or orange. So let's give it green for now. And this is green, orange. Okay.
We can give red here. B to D.
Yes,
Red.
we can give red here.
And
Now
G to
we
G to
or
B we can give green.
green. We have to give green because we have used all three colors. And for this now green, red. So let's give it blue. And if we give it orange, so we see that we are able to color it with 4 colors. So chromatic index is also 4. So sorry, chromatic index is 4, chromatic number was 3. Now this graph. So what is the chromatic index for this graph? So maximum degree is
3.
3. So what is the chromatic index? So let's try to give 3 colors. So we'll look. So we'll we'll look at the maximum degree vertex. So this is a maximum degree vertex. We'll give all three different colors: red, blue, green. Now this has been given red, blue, green. So now
Blue.
blue, let's give it blue.
Mm,
No, we
blue is
cannot give
not
it to blue.
possible.
No,
Blue,
no,
blue is
blue.
not
Red,
possible. We
red,
have to
red.
give it red.
Cross edge blue.
We have to give it red. Blue is not possible. Yes. Now for this one, we have to give green because red
Green.
is there, blue is there, green. So now for this one, we have to give blue.
Blue.
But for this
Blue.
one, we
Not
cannot give
possible.
red, we cannot
Blue.
give blue, and we cannot give green. So we'll have to give another color which is orange. So we see that we need at least four
Four.
colors. So chromatic index is 4. And what about chromatic number?
3.
3. So we can, this was easily one, like you can give it like, so basically red, or we can like see, you can see that it is 3. Uh, so this was for today. If you have any quick questions, you can ask. Yes.
Ma'am, I didn't attend actually the previous sessions at all. I have a doubt in one assignment, ma'am. In a graph, they have given the last edge as find the augmenting path for the last edge. So augmenting path means alternatively it must have non unmatching and matching.
Yes.
How can we in the solution part they have given there exists an augmenting path? I couldn't
Last,
understand.
okay, last, so can you tell me the assignment number? Like,
I think it is 3 or 4. I don't remember. Sorry.
wait, okay. So,
Augmenting path, just for not in the flow graph. Before that, in the
Matching.
matching. I
matching.
don't remember the assignment exactly.
Okay, so I think, okay. So, can you
Any
explain
graph that has a last edge, that may be a pendant edge. So
last
how
edge as
can
in
we
last
uh,
edge?
last edge that is a pendant edge. So how can we write an augmenting path for that particular edge? But the
Okay, so
solution
see,
part they
yes,
have
yes,
given is
yes,
yes.
yes. So sometimes maybe that is the confusion. So basically, if you have an augmenting path, so it has to start with, so your augmenting path can have just one edge also. So basically,
Edge also.
one edge also. So so if it is a pendant edge, so you can take some edge, you can take some edge with non-matched, in which both the vertices are non-matched. Then that will be an augmenting path with respect to that edge. Do you understand what I'm saying?
No,
So I'm
ma'am.
saying, so
Uh,
suppose, okay, I think this is your question. If I say, suppose some graph is like this, okay, so this is the kind of edge you are
exactly.
saying, right?
Exactly.
A,
Yes.
B, C, D. And CD is your edge.
Edge.
Now you are asking if there's a augmenting path.
Augmenting path.
So AB will be an augmenting path. Because what is the definition of augmenting path? It should start with an unmatched vertex, end with
Uh,
an unmatched vertex, and alternate between matched and unmatched edge. So A
uh,
is an unmatched vertex, B is an unmatched vertex, and AB is an unmatched edge. So it is a just path with one vertex, just path with
yeah.
one edge.
Okay.
Okay, is it clear?
So the path between unmatched.
Yes. So
Okay.
basically, so your augmenting path can just have one edge only. In
Okay.
if both the vertices are unmatched.
Unmatched. Okay. Yeah, that's because in the definition they have given unmatched, then matching, then unmatched. It
Huh?
must become alternatively. So I got confused how
Yes.
it is possible.
Yes. 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 But when they mean alternatively, that means we are including the case of one edge
My
also.
same mistake I did.
Yeah.
Same mistake I did.
Huh.
That is
Okay.
unmatched vertex. We start with unmatched vertex. with unmatched vertex and end with unmatched vertex.
Yes.
That's all.
That's all.
Uh,
Yes. That's all.
AB here is
Hmm.
ma'am is asking whether we have to see about unmatched set pair, then matching pair, and then unmatching pair.
Yes,
First
yes,
we
yes.
thought like that.
Yes, yes, yes. That
Uh,
is so. So if it has more than
that is
one
also
edge,
possible.
yes. If it has more than one edge,
But
then
here
you
it
look
is
at
only
alternatively.
yes,
But this case is
only one
also
edge means we have to see the
yes,
unmatched vertex ends with unmatched vertex. Then it
yes.
is a augmenting path.
No, no.
Yes.
Huh. So no, no. We have unmatched word. So it should start with unmatched vertex, end with unmatched vertex, and alternate between unmatched and matched edge. But if there is so second property should also be true if it has more than one edge. Okay.
Okay. Yes, ma'am. Yes, ma'am.
Yes.
Thank you so much, ma'am. I had a doubt. Thank
Yes.
you.
Yes. Okay. Okay. Any more doubts?
Thank you, ma'am. You taught us excellent, ma'am. Thank
Okay.
you, and we wish you that you finish your PhD, and then we will do PhD under you.
Okay. Yes. Sure. All the best to you for your exam too.
Thank you so much, ma'am. Really
Thank you,
had a
ma'am. Thank you.
wonderful session with you. Thank you.
Okay. Okay.